Hello to everyone. In today's video, we are going to be looking at exact differential equation. Under exact differential equation, we are going to be using the idea of the product rule. We know that from the product rule, the derivative with respect to x of a product uv is the same as u dv on dx plus v du on dx. So now, in order to solve the differential equation using the exact method, we have to know that the opposite of differentiation is integration. So basically, when we have this, it means that this is going to cancel out with this one. So now we're going to move to an example. Now this is our example that we are going to be looking at. We have our differential equation. Now if we look at this, if we look at the left hand side of this differential equation, we have dy on the x plus y. There's something peculiar about this differential equation. We see that the derivative with respect to x of xy is, so we want to find out what this is. So you are the one to figure out this term or this product. So basically, if we keep x constant and we differentiate y with respect to x, we are going to have dy all over dx plus, now if we keep our y constant and we differentiate x with respect to x, we're going to get 1. So this will simply be equals to e to the power x. So clearly we see here that the derivative of xy is the same as this, as the left hand side. Therefore, instead of writing x dy dx plus y, we're going to write d all over dx of xy equals to e to the power x. So this is very clear. What we are going to do now, we take our integral sign on both sides. When we take our integral sign on both sides, then we know that this is going to cancel this, obviously. So we'll be left with xy equals to the integral of e to the power x. So we have xy equal to the integral of e to the power x is e to the power x plus our constant k. So we are going to have our y. So definitely we are going to have our y to be equal to e to the power x divided by x plus k divided by x. So this is our solution. This is our solution. Now I'm going to move on to the second example. Okay, now this is our second example. So looking at the left hand side, we want to look for a product, so that when we take the derivative of that product, it should give us the terms, the exact terms on the left hand side. That is why it's called the exact differential equation. So now from try and error or guessing, we have d all over dx of x squared sine y. So this will be equal to 1 all over x squared. So basically I haven't changed anything, that's the same. Now if you try and it doesn't give you, you have to just change a term and you try again. At the end you compare if it's going to give you the exact term that is on the left hand side. So here, if we keep our x constant, we're going to differentiate this function with respect to x. Now if we keep our x squared constant and we differentiate sine y, then we're going to have cos y and then dy all over dx, because we're differentiating with respect to x. Now plus, if we keep our sine y constant, we keep our sine y constant and we differentiate x squared, we're going to have 2x. So this will be equal to 1 all over x squared. So clearly we see here that this looks exactly like our differential equation. Therefore, instead of writing this whole differential equation or the two terms, I'm simply going to write the derivative with respect to x of x squared sine y equal to 1 all over x squared. I haven't changed anything actually, so if I take my integral sign on both sides, then here this is going to cancel this. I'll be left with x squared sine y equals to the integral of, now this is 1 all over x squared. I can write this as x to the minus 2. So I differentiated this with respect to dx, with respect to x. So we're going to have our x squared sine y to be equal to, now here, since we're integrating, this will simply be equal to negative 1 divided by negative 1 plus our constant k. Therefore, our sine y will simply be equal to negative 1 all over x cubed plus k all over x squared. So that our y finally will simply be equal to the sine inverse of, not that, the sine inverse of negative 1 all over x cubed plus k all over x squared. So that's our solution. So on to the third and the last question under exact differential equation. Now looking at this question, we see clearly that we want to express the left hand side as a product. Therefore, the first thing we need to do is we try to see if we are going to look for a derivative of this function. We look for a function which, when we take a derivative of that function, let's say the function should be y squared e to the power x, should give us all of these. So normally this is e to the 2x. So let's try to express this, look for the first derivative of this function and compare with what we have on the left hand side. If it's the same, then we can proceed from there. So if we keep our y squared constant here, if we keep our y squared constant and we differentiate e to the power x, we are going to have e to the power x. Now, plus if you keep our e to the power x constant and we differentiate our y squared, we are going to have 2y. Since we are differentiating with respect to x, we are going to have dy all over dx. So clearly we see here that this looks exactly like what we have above here. We have 2y e to the power x, that is it, dy dx plus that. So instead of writing this as usual, we are simply going to write our d all over dx of y squared e to the power x equal to our e to the power 2x. So from here we take our integral. So if we take our integral on both sides, we're going to have, we see that this is going to cancel with this. We'll be left with because if we multiply through by dy, simply we're going to have y squared e to the power x equal to the integral of e to the power 2x dx. Now there's a general rule: when we're integrating we divide, and when we're differentiating we multiply. So we have our y squared e to the power x here equals to, we have the integral of e to the 2x dx. So we are going to differentiate the power, we are going to have 2. Since we're integrating, we'll have to divide, so this is going to be a half. Then we copy the same function 2x plus our constant of integration k. So our y squared will simply be equal to e to the power 2x divided by 2e to the power x plus k divided by e to the power x. So here we're going to have our y finally to give us the square root of a half. So here we have e to the power x and e to the 2x. So from logarithm, this is going to give us e to the power x plus k divided by e to the power x. So basically that is our solution. So guys, that is all for the part 3 of this video series. The part 1 was about solving differential equation by separating variables, and the part 2 was solving homogeneous equations. So if you haven't checked that part 1 and 2 out, I'm going to put the links of those videos in the description box and in the comment section, and even above the video somewhere there, so that you can click on it and you get right to the video. So the part 4 and 5 of this video series is still coming up. So for those interested in getting more, you can simply subscribe to my YouTube channel, and if this video was helpful in any way, you can just give a thumbs up, a like. It's going to help the channel. Thank you very much, and see you in the next video.